Hello there. In this video, we're going to discuss the basic principles associated to what we call joint probability mass functions. So recall, let us assume if you roll, a couple pairs of die, namely, let's assume the first one has the numbers 1, 2, 3, 4, and 5. And let's assume the second die contains the values, say 1, 2, 3, 4, 5, 6, and 7. So in the previous context of sort of how we approach problems similar to these structures is we consider a variable, say s, which could be, say, the sum of the values x and y. Therefore, the sum contains the values 2, 3, 4, up to 7 plus 5, which is 12. And we discuss the probability of values associated to the values in the set S. So in this case, we're going to consider probability functions on two variables and not just one. And we'll explain a couple other things, namely called marginal distributions, along with that as well. All right, so what we're going to do is we're going to construct what we call joint probability mass functions. So we're assuming that the variables of this function are, of course, discrete, hence why we call them mass functions. So we're going to consider the function pxy. So it's a function of 2, and it could be more variables, of course. So this expression is equivalent to the simple probability that random variable x is equal to x and the random variable y is equal to y. So this is the equivalent statement in terms of simple probabilities of this probability joint mass function. So the domain of this joint probability mass function, of course, is going to be the Cartesian product of x cross x. So if we use the example above, it's going to be the set of all pairs of numbers, say 1, 1, 1, 2, all the way down to 1, 7, and we continue this all the way down to, say, 5, 1, 5, 2, all the way down to 5, 7. So it's the set of ordered pairs where the first element comes from x and the second one comes from y. All right, so a couple properties that are going to be associated to probability joint functions are going to be similar to the ones for single variable functions. So the first one is the sum across all x and all y of this probability joint mass function is, of course, have to be equal to 1. And 0 is less than or equal to the probability of xy. And that's going to be less than or equal to 1, and this has to be true for all x, y in the Cartesian product of x and y. All right, so let us assume we're interested in the value of p23, where p is defined on the sets where I have a 5-sided die for x and a 7-sided die for y. So this is, of course, equal to the probability that x is equal to 2 and the probability that y is equal to 3. So we're going to assume that the likelihood of the probability of x is equal to 2 and y is equal to 3 are independent and also equally likely. So if these are independent events, then we know that this is the same as the simple probability that x is equal to 2 times the probability, or the simple probability, that y is equal to 3. So the probability that x is equal to 2 if all of the sides are equally likely, so that's going to be equal to 1/5, and the probability that y is equal to 3 is going to be 1/7. So the value of p23 is going to be equal to 1/35. And that's pretty much how to evaluate joint probability mass functions if you know the distributions of, say, x and y. So another example, let's assume we define a probability mass function p on two sets x and y So let us assume x has the values 1 and 2, and let's assume y has the values 1, 2, and 3. So let's assume that the values are as follows. Say 1/20, 2/20, 5/20, 5/20, 6/20, and 1/20. So one could ask, is P a joint probability mass function on the random variables x and y? So you sort of have to test those two properties. So the sum across all x and x and the sum across all y and y is going to be equal to, so that's going to be 1/20 plus 5/20 plus 6/20 plus 2/20 plus 5/20 plus 1/20. So of course all have a factor of 120, so we have 1 plus 5 plus 6 plus 2 plus 5 plus 1. So 1 plus 5 is 6, 6 plus 6 is 12, 12 plus 2 is 14, and 14 plus 1 is 15, plus 5 is 20. So this is 1/20 of 20, which is equal to 1. So that property checks out. And of course, all x and y satisfy pxy is in the interval 0, 1. Actually, it's open interval 0, 1 because there's no values in this set that have a probability of 0 or 1. So therefore, P is a joint probability mass function. So that's good. All right, so now recall, we know a lot of properties associated to single variable functions, and sometimes it's not necessary to define a whole entire new set of concepts. So the one concept that's sort of going to bring together the single variable case and the multivariable case is what we call marginal probability mass functions. Marginal probability mass functions. And the definition of marginal probability mass function or our marginal PMFs is the following. So the marginal PMF of P for the variable x, for some value x and x, is going to be equal to the sum of all values y and y of P x yk. So we're going to sum up all of the values in y, and that's going to give some value for x. And similarly, the probability marginal function for y, for some value y, is defined to be equal to the sum of all xk and x of the probability of xk, comma y. So let's do a quick example of how to construct the marginal PMFs. So example. Let's assume we're interested in the following. So let's recall that distribution I defined above. So Pxy with the values 1, 2, 3 for y, 1, 2 for x. So what was that? 1 over 20, 5, 6, 1, 5, and 2. So we've already verified that P in this case is a probability joint mass function on x and y. So let's calculate its marginal probability mass functions. So let's start with the function x. So Px of x is defined, again, to be equal to the sum of all yk and y of Px yk. So that means this is going to be equal to the probability of x comma y1, which is 1, plus the probability of x comma 2, plus the probability of x comma 3. So when x is equal to 1, well, when x is a variable and y is equal to 1, what do we have? So in expanded form, this is the definition of the marginal PMF for x. So if we look at some values, so what are the possible values of x? So x can be either 1 or 2. So when x is 1 or 2, what is the value of the probability marginal function for variable x? So px of 1 is going to be the value of p11 plus p12 plus p13. So if we look at our table, p11 is going to be that, p12 is going to be that, and p13 is going to be that. So 120, 520, 620. 120, 520, 620. Added together, so that's going to be 5 plus 1 is 6, but 6 plus 6 is 12. So this is going to be 1220. And if I want to find the marginal PMF for x at 2, that's going to be p21 plus p22 plus p23. So keep in mind, for the marginal PMF for a variable, we sum over the values of the other variable of the PMF. So what was that? So p21, p22, and p23. So that's going to be 220, 520, 120, 251. So 2, 5, 1. So that's going to be 5 plus 2 is 7 plus 1 is going to be 8. So that's going to be 8, 20. So these are the values for the marginal PMF for x, for the joint probability mass function p of x and y. Now, keep in mind, notice that this and this are between 0 and 1, and also the sum of these two probabilities is also 1. So let's do another example. Let's assume we want the probability marginal function for variable y now. So by definition, that's going to be the sum across all xk and x of p xk y. So keep in mind, this is the joint probability mass function on the right, and this is the marginal probability mass function for y on the left. So all of the values for x, of course, are only 1 and 2. So this is going to be p of 1 comma y plus p2 comma y. So this is the implicit representation of the marginal PMF for y. So if we go back to our value, what is the possible values of y? So y can take values 1, 2, and 3. So the marginal PMF of y is going to take 3 values as well. So if we go back to this, so when y is equal to 1, what do we have? So when y is equal to 1, we have py of 1 is equal to p11 plus p21. And if we go back to the table, that's going to be 120 plus 220, which is 320. If we want py of 2, that's going to be p12 plus p22. And if we go back to our table, that's going to be 520 plus 520, which is 1020. And if we want py of 3, that's going to be p13 plus p23. If we go back to our table, it's going to be 620 plus 120, which is 720. As before, all of these numbers are between 0 and 1, and also the sum of these values are equal to 1, which brings us to a useful property. So, property that's useful. The marginal PMFs, Px and Py, are also probability mass functions. And remember, these are what we call marginal PMFs for P. And sometimes we rewrite this as P of x comma y, so that you know that it's of those two variables. And a couple additional properties to discuss that is interesting. And we'll talk about more of these later. So the joint probability mass function of pxy x comma y, is the same as the simple probability that x is equal to x intersection the value that y is equal to y. So if we remember our simple probability rules, this is the same as the probability that x is equal to x times the probability that y is equal to y, assuming that x is equal to x. So now we're talking about expectational values, or you could do it in the other direction. It's the same as the probability that y is equal to y times the probability that x is equal to x, assuming that y has taken the value of y. So this is using the definition of conditional probabilities. So this is one useful connection. And you can get the following as corollaries, namely, the simple probability that y is equal to y, assuming that x is equal to x, can be found by taking the joint probability mass function of x and y and dividing that by the marginal probability mass function of x. And you can also get a similar representation for this as well. And we can also get the following property, that if x and y are independent, then pxy of xy is equal to pxx times pyy. Hope you enjoy.